So this next video is on recursion. And recursion is actually a pretty simple concept to understand, but it can get a little difficult to actually think about and implement. Um, the way the recursion works is it's pretty much a function that calls itself. And what that means is we think we can if we have an algorithm that is basically doing the same thing over and over again, we can have that algorithm call the function that that algorithm is defined in, and so it will keep calling itself over and over again, and run that algorithm over and over again. Of course, when you do that, you do risk the fact that you can actually get infinite loop, right? Because if the function keeps calling itself, then what's going to stop it? So you do have to have a base case in order to stop your function, your recursive call. All right, and so I'm going to give an example of what a recursive function will look like. Just 1 second. Let's think about the factorial algorithm, right? The factorial is pretty much defined like this. And of course, I am not a mathematician, so if I get this wrong, I apologize. But it's pretty much, if I wanted to do n factorial, it's something like this: n times n minus 1 times n minus 2 all the way to 2 times 1. That would be factorial. So if I wanted to write a function, notice that this is kind of doing the same thing. It's just multiplying the number times the number previous to it, right? And you know, of course, we could do that in reverse. We could say it's multiplying the number times the number times the next number. So if we wanted to find, let's say like 5 factorial, right? That could be equal to 5 times 4 times 3 times 2 times 1. Of course, it could also be 1 times 2 times 3 times 4 times 5. Right? So if we wanted to do a factorial, a recursive call to a factorial function, we can do that quite easily, right? We can create our function, and let's say our function is just going to return an integer. We could do something like this. We'll call it factorial. And factorial will take an integer. And this is basically the number that we want to find in factorial. So if I want to find a factorial 5, I would send the number 5 to my function. All right, so I could do something like this, right? Return num times factorial x, num minus 1. Right, and let's just kind of trace that. If I do something like that, I have, so let's say inside my int main, I do something like factorial 5. So when I send factorial 5, then it's going to return 5 first. It's going to return 5 times, right? And then it's going to do num minus 1. So then that's going to return 4. Right? And then when we go back now, num is 4. So it's going to return 4 times 3. Right? And it'll keep doing that. Now, since num is 3, num minus 1 is going to be 2. So it's going to send that back to the uh, factorial function. And now num is equal to 2, so it's going to send num minus 1, and that's going to be 1. And then I hope you all noticed I am never going to stop. This algorithm is never going to stop, right? Because then the next thing it's going to do is bring in -1, and we actually don't want this, right? So that's why we need to have a stopping case. If we let the function the way it looks here, we will get an infinite loop because there's nothing that is stopping this function from returning. So that's why I left a little space up here. So what we want to do is put our stopping case, right? And when do we want to stop? We want to stop when the number is equal to 1, right? So when we get the number equal to 1, that's when we want to stop. So we can just put a really simple stopping case in there. We can just say if num, if num is equal to 1, then we're just simply going to return 1. That's all we need to do is return 1. Right? Otherwise, we would just return num. We return num, and then we'll do our recursive call. And so now this would not happen because as soon as we hit 1, it's going to return 1, and it's no longer going to call the factorial function again. And so we'll actually get our result. All right, so let's just do another example. I hope we're all familiar with the Fibonacci sequence. The Fibonacci sequence basically is something like it usually it depends on how you where you see the Fibonacci sequence. But usually it's defined like this. So it'll be 1, and then 1, and then 2, and then 3, and then 5, and then 8, and 11. Excuse me, not 11, 13. And basically what it is that the number is the sum of the two previous numbers. So 2 is the sum of 1 plus 1, right? 3 is the sum of 1 plus 2. 5 is the sum of 2 plus 3, and so forth, so on. So we can write our Fibonacci sequence, right? Since we know that, n, I don't know how to write that in mathematics term, but we know that the nth number of the Fibonacci is the sum of n minus 1, n minus 2, right? So I don't really know how to write that in mathematical terms because it's been a while since I've taken math, but I illustrated it here, what that is. So let's look at that inside our recursive function, right? So I'm going to write int Fibonacci. Of course, that's going to take in integer. Just call it n. Of course, if we know that the number then is going to be the sum of the first two numbers, then I'll just return, right, the Fibonacci numbers, the two Fibonacci numbers prior to the number that I'm looking for, right? So that means I'm going to call my Fibonacci function, Fibonacci, right? And the sum of the two numbers prior to that, so that's going to be n minus 1 plus the Fibonacci number of n minus 2, right? And that's pretty much the Fibonacci sequence, right? That's what the Fibonacci defines. The nth number in the Fibonacci sequence is the nth minus 1 number plus the nth minus 2 number. And so that's exactly what we wrote here in our Fibonacci sequence. right? But of course, just like the previous example, this will never stop if we don't have a uh, stopping case. So what is our stopping case, right? Our stopping case is, if you notice, right, the first sequences in our Fibonacci is 1, right? Um, so we can say if n is less than or equal to 1, then we want to actually just return whatever that number is. And then that will actually compensate for the cases where you see 0, because sometimes some people say that 0 is in the Fibonacci sequence. So we pretty much just write this: if n is less than or equal to 1, then we simply return n. Right? Otherwise, we just do our recursive call to the Fibonacci sequence. So I encourage you to don't just trust me. I wrote the code down here. Try to copy this code and see if it works. It will work though. All right, and so that's pretty much um, recursive calls. I want to mention that our secret word today is glass, and just to do a quick summary of recursive calls. So recursion summary. All right. So basically, we use recursion if we are able to find if we see that the problem that we're trying to solve is actually just smaller instances of the same problem, right? We see that Fibonacci is just the Fibonacci number plus, the two Fibonacci numbers prior to the one that we're looking for. So we see that it's doing the exact same thing. So I will say we can use recursion if we notice that our problem can be broken down to smaller instances of the same problem. All right, again, that's we can use recursion if we notice that that our problem can be broken down to smaller instances of the same problem. So also with recursion, we must have two cases, or at least two cases. Right. The first is going to be our stopping case, and that is pretty much how we make sure that our recursion is going to stop and that we're not going to get a infinite loop. Right. And usually our stopping case will not call, right? It will not call the function again. All right, and then we also have our recursive call. I don't know why my pen is not working well right now. And this call will call the function again. Yeah, so those are like the really main things that we wanna know about recursion. So yeah, thank you for watching, and I hope this helps.